The aircraft is already in flight. There is no clear beginning, only continuation. A steady forward motion through air that cannot be seen, only inferred through vibration, engine tone, and the faint resistance against the structure. Outside, the sky is uniform. There is no horizon, no visible separation between Earth and atmosphere. Only a dense, indistinct field of gray, laid in subtle gradients that offer no reference, no distance, no scale. The aircraft moves through it without deviation, at least none that can be easily perceived. Inside the cockpit, the environment is narrow and functional. Metal framing, glass panels lightly clouded at the edges. Instruments arranged in a pattern that suggests order, though not certainty. Needles move, but not all of them agree. A compass, sensitive to even slight disturbances, drifts almost imperceptibly. The altimeter holds steady, for now. The A-speed indicator trembles, not from turbulence, but from the inherent instability of the system itself. There is no artificial horizon. There is no independent confirmation of attitude beyond what the pilot believes the aircraft is doing. The engine continues at a constant rhythm, a radial configuration. Its pulses are uneven by design, a mechanical cadence that fills the cabin space. Each combustion cycle is felt as much as it is heard. It is not smooth, but it is consistent. And in this environment, consistency is interpreted as reliability. Below, the terrain is concealed, not by darkness alone, but by cloud, low, dense, and continuous. There are no brakes, no lights, no indication of elevation or distance. If the aircraft descends, there will be no visual warning. Only impact will define the boundary between air and ground. Navigation is not guided by external systems. There are no radar vectors, no satellite positioning, no continuous radio navigation, only estimation. Heading is maintained through compass reference. Position is calculated through time, speed, and directional assumption, dead reckoning. A method that does not confirm where the aircraft is, only where it is believed to be. Wind, invisible and variable, alters that belief. A slight crosswind, unmeasured, unnoticed, can shift the aircraft miles off its intended course over time. Not abruptly, not dramatically, but enough. The cockpit does not reflect urgency. There are no alarms, no flashing indicators, no abrupt changes in engine tone. Everything suggests normal operation. And yet, normal operation in this environment is dependent on alignment between assumption and reality. A divergence between the two does not announce itself. It accumulates, gradually, silently. The aircraft continues forward, maintaining altitude, maintaining heading, according to its instruments. But the instruments themselves are limited. Some are delayed. Some are affected by pressure variations. Some respond to forces that are not immediately apparent. Without external reference, interpretation becomes judgment, and judgment, in the absence of confirmation, becomes vulnerability. Moisture begins to form along the edges of the wings, not visible from the cockpit, but present, a thin, uneven layer, ice. At first, it is negligible, a slight alteration in airflow, a marginal increase in drag. The engine compensates without instruction, but the accumulation continues. Lift characteristics begin to change, not dramatically, but subtly enough to affect control margins. The aircraft remains stable, but stability now requires more precise input. The margin for error narrows. Still, nothing in the cockpit demands attention. There is no warning system for icing, no automated correction, only the gradual shift in how the aircraft responds. The compass shifts again, slightly, not enough to prompt immediate correction, not enough to appear incorrect, but enough, over time, to redefine the aircraft's path. Below, the terrain rises. Not sharply, not visibly. A gradual elevation change, hills transitioning into higher ground, obscured entirely by cloud. The aircraft, maintaining its assigned altitude, does not account for terrain it cannot detect. There is no terrain awareness system, no predictive alert, only altitude above sea level, an abstract measurement, disconnected from what lies directly beneath. The difference between safe clearance and controlled flight into terrain is not measured in hundreds of feet. Sometimes it is less. The engine continues, steady, uninterrupted. Its reliability becomes a constant in an environment defined by uncertainty. Time passes without clear markers. Minutes extend without distinction. Each moment appears identical to the last. There is no visual progression, only continuation. The aircraft is no longer where it was calculated to be. The deviation is small, but cumulative. A shift in heading, a slight miscalculation in wind correction, an assumption carried forward without verification. The result is not immediate. It is developing. The first indication is not a warning. It is a subtle inconsistency, a discrepancy between expected position and elapsed time, a landscape that does not appear, because nothing appears at all. Only cloud, only instrument readings, only interpretation. The aircraft begins a gradual descent, not abrupt, not alarming, a controlled adjustment based on expectation. Expectation that the terrain below remains at a known elevation. Expectation that position has been maintained. Neither assumption is confirmed. Both are critical. The descent continues. The margin between aircraft and terrain, unseen, undefined, reduces steadily. There is still no visual reference, no horizon, no ground, no indication of proximity. Only the instruments, only the belief that they are sufficient. And for a time, they are, until they are not. Aviation, in its early decades, was not yet a system. It was a collection of capabilities, some reliable, many experimental, assembled into a method of transport that functioned, but not always predictably. By the 1920s and 1930s, powered flight had moved beyond novelty, yet it had not reached consistency. Aircraft could cross distances that had once required days, but they did so without the infrastructure that would later define safety. Navigation was not guided, it was inferred. Pilots relied on dead reckoning, a method built on three variables: heading, speed, and time. From a known starting point, a position was calculated forward. Every correction depended on the assumption that previous calculations were accurate. Wind complicated that assumption. Unlike modern aviation, where wind speed and direction are continuously measured and updated, early pilots often worked with estimates, sometimes outdated, sometimes incomplete. A crosswind, even a mild one, could push an aircraft laterally without any immediate indication. Over the course of an hour, that displacement could become significant, but the system offered no automatic correction. There were no ground-based tracking systems monitoring position, no continuous radio guidance adjusting course. Only occasional checkpoints, rivers, railways, towns, visible from above. When visibility was lost, so was verification. Weather forecasting, in this period, was limited. Meteorological understanding existed, but its application to aviation was still developing. Reports were regional, often delayed, and rarely precise at altitude. Cloud layers, in particular, pose a distinct challenge. From the ground, they appeared static. From within, they removed all orientation. Pilots entering dense cloud encountered a phenomenon that was not yet fully understood: spatial disorientation. Without a visible horizon, the human body cannot reliably determine attitude or motion. The inner ear, responsible for balance, can produce false sensations, suggesting level flight during a bank or descent during level flight. In modern aviation, this limitation is mitigated by instruments. In early aircraft, those instruments were incomplete. The artificial horizon, which provides a direct indication of aircraft attitude, was not widely available or standardized. Some aircraft operated without it entirely. Instead, pilots relied on indirect cues, turn indicators, airspeed trends, engine performance, and, critically, intuition shaped by experience. These methods worked until conditions exceeded their limits. The aircraft itself was a product of transitional engineering. Many designs of the era still incorporated wooden fabric construction, supported by wire bracing. Metal A-frames were emerging, but not yet universal. Structural strength was sufficient for expected loads, but margins were narrower than in later designs. Engines, typically radial and air-cooled, were robust in concept but variable in execution. They did not fail often without warning, but when they did, redundancy was limited. Multi-engine aircraft provided some margin, but performance with one engine inoperative was often marginal, especially at altitude or in poor weather. Carburetor icing, another poorly understood hazard, could reduce engine power gradually, without clear indication. Again, the theme was not sudden failure. It was gradual degradation. Air routes, where they existed, were loosely defined. There were no standardized airways in the modern sense. Some regions used lighted beacons, rotating lamps placed along key routes, to guide pilots at night. But these were limited in range and dependent on visibility. In poor weather, they disappeared entirely. Radio communication was available, but not continuous. Transmission ranges were limited. Signal clarity varied, and procedures of communication were still evolving. A pilot could report position, but that position itself might already be uncertain. Air traffic control, as a coordinated system, did not yet exist. There were no controllers issuing vectors, monitoring altitude, or separating aircraft. Each flight operated largely in isolation. Responsibility for navigation, terrain clearance, and weather avoidance rested entirely within the cockpit. Training reflected these realities. Pilots were skilled, often exceptionally so, but their training emphasized visual flight, flying by reference to the ground, maintaining orientation through sight. Instrument flying, where the pilot relies solely on cockpit instruments, was not yet standardized. Those who attempted it did so with limited tools and minimal procedural guidance. It required discipline and carried risk. The culture of early aviation also played a role. Flight was still seen as demanding, even heroic. Pilots were expected to operate in conditions that would later be considered unacceptable. Delays were costly. Diversions were uncertain. Turning back was not always a preferred option. This did not reflect recklessness. It reflected the absence of alternatives. Against this backdrop, the flight in question was not unusual. It followed a route that had been flown before. It operated within the known capabilities of the aircraft. It departed with an understanding, shared by pilot and operator, of the risks involved. Nothing in its planning indicated inevitability. The weather, while imperfect, was not extraordinary for the region. The aircraft was functional. The pilot was qualified within the standards of the time, and yet the system it relied upon contained gaps, not obvious in isolation, not critical on their own, but capable, when aligned, of producing conditions where error could develop without detection. The environment did not need to be extreme, only ambiguous. The aircraft did not need to fail, only to respond differently than expected. The pilot did not need to make a single critical mistake, only a series of small, reasonable decisions, each consistent with the information available at the time. This is how early aviation accidents often unfolded. not as abrupt events, but as progressions. Aviation, at this stage, had achieved flight. It had not yet mastered certainty. The accident does not begin at the moment of impact. It begins within the structure of the system itself, distributed across machinery, training, environment, and expectation. Each element functions within its limits. Together, those limits begin to overlap. The aircraft is not experimental. It is representative of its time, designed within the boundaries of available materials, engineering knowledge, and operational demand. A single or twin-engine propeller-driven configuration. Radial engines mounted forward, exposed to airflow for cooling. The fuselage constructed either of metal framing or reinforced wood, covered in fabric or thin aluminum skin. Its performance is adequate. Cruising speed is modest. Climb capability is sufficient under normal load. Control response is stable, predictable within clear conditions. But predictability depends on environment. Instrumentation inside the cockpit reflects the transitional nature of the era. There is no integrated system. Each instrument operates independently. The altimeter, driven by static air pressure, indicates height above sea level, not terrain. The compass, susceptible to magnetic variation and aircraft movement, provides heading, but not stability. The airspeed indicator, relying on pitot pressure, reflects forward motion, but can fluctuate with airflow irregularities. There is no redundancy, no cross-check system that confirms one reading against another with certainty. And critically, there is no reliable, continuously available attitude reference. Without an artificial horizon, the aircraft's orientation in space cannot be directly measured, only inferred. In clear conditions, this limitation is manageable. In cloud, it becomes central. The aircraft is also vulnerable to environmental accumulation. Ice forms gradually, not as a visible obstruction, but as a thin, uneven layer along the leading edges of wings and control surfaces. This alters airflow. Lift decreases. Drag increases. Stall speed rises, without any direct indication. The aircraft continues to fly, but its margins narrow. The engine, while consistent, is not immune. Carburetor icing can reduce power subtly. Fuel-air mixture shifts with altitude and temperature. Performance changes are gradual, not abrupt. The aircraft does not fail. It adapts imperfectly. Crew. The pilot is trained within the standards of the time. Experience is measured not only in hours, but in exposure, routes flown, conditions encountered, decisions made without external support. There is familiarity with uncertainty, but familiarity does not eliminate risk. Training emphasizes visual navigation, maintaining orientation through reference to terrain, horizon, and known landmarks. Instrument flying exists, but as a skill, not a system. Procedures are limited. Standardization is minimal. Flying in cloud requires interpretation, not just of instruments, but of what those instruments might mean under imperfect conditions. There is no formalized crew resource management. If a second crew member is present, roles are loosely defined. Communication is functional, not procedural. Decision-making remains centralized. The pilot assesses position, weather, aircraft performance. But each assessment depends on inputs that may already be degraded. There is no external correction, no controller monitoring deviation, no system providing alerts. Confidence, therefore, becomes part of the operational environment, not overconfidence, but necessary confidence, required to continue flight in conditions that offer limited verification. The pilot does not act without reason. Each decision is aligned with available information. The limitation lies in the information itself. See environment. The environment is not extreme. It does not present as a storm of unusual severity. There are no violent updrafts, no visible structural threats. Instead, it is consistent. Low cloud cover extends across the route. Visibility is reduced, not to zero, but below the threshold required for visual navigation. The horizon is absent. This absence is significant. Without a visible horizon, orientation must be constructed internally, through instruments and perception. Both can be unreliable. Wind exists at altitude. Its presence is not dramatic, but it is variable. A steady crosswind, uncorrected or underestimated, shifts the aircraft laterally. Drift accumulates over time. The aircraft remains on a heading, but not on a track. Below the cloud layer, terrain rises gradually, not sharply enough to create a meteor hazard, but enough that altitude margins, calculated from expected position, begin to erode. There are no visual cues, no lights penetrating the cloud, no terrain features breaking through. The aircraft flies above an unseen surface that is slowly approaching. Temperature conditions support icing. Moisture in the cloud adheres to the aircraft structure. Accumulation is uneven. Performance degradation is subtle, but continuous. The environment does not confront. It conceals. These systems, the broader aviation system, at this stage, is incomplete. Navigation infrastructure is fragmented. Radio beacons, where available, are limited in range and reliability. Signal interpretation requires skill and is subject to interference. In many areas, they do not exist at all. There is no continuous positional tracking. The aircraft is not monitored from the ground. Its progress is assumed based on departure time and estimated speed. If deviation occurs, it is not immediately detected. Communication systems provide intermittent contact. Transmissions are brief. Reception is inconsistent. There is no real-time correction. Weather reporting is similarly constrained. Conditions at departure may not reflect conditions en route. Updates are infrequent. There is no onboard radar. No forward-looking system capable of identifying terrain or weather formations. Air traffic management, as a coordinated system, is absent. There are no assigned altitudes designed for terrain clearance. No enforced separation standards. Each flight operates independently, guided by procedure only where procedure exists, and where it does not. Judgment fills the gap. Intersection of factors. Individually, none of these elements guarantees failure. The aircraft is capable. The pilot is competent. The environment is manageable. The system, though limited, is functional. But the interaction creates dependency. The aircraft depends on accurate interpretation. The pilot depends on reliable instruments. The instruments depend on stable conditions. The conditions undermine all three. The result is not instability. It is misalignment, a gradual separation between perceived reality and actual position. No single moment defines the start of the accident. It develops, quietly, within normal operation. There is no single moment where the flight becomes unstable. The aircraft remains under control. Its attitude is steady. Its engine continues without interruption. Its instruments, within their limits, still provide readings. What changes is alignment. The aircraft is no longer where it is believed to be. The descent begins as a routine adjustment, a controlled reduction in altitude, calculated from expected position along the route. There is no urgency in the action. It is procedural. Altitude is reduced to align with what should be lower terrain ahead. A standard practice based on planning, not direct observation. The altimeter responds predictably. Numbers decrease in steady increments. The descent rate remains within normal limits. There is no indication that the assumption underlying this action is incorrect. Outside, the cloud layer remains unchanged. Visibility does not improve. There are no breaks, no shadows, no light gradients that suggest proximity to the ground. The aircraft moves through uniform gray. Without visual reference, altitude becomes an abstraction, a number, detached from physical reality. The compass holds a steady heading, but the heading itself is no longer aligned with the intended track. The earlier drift, subtle, uncorrected, has shifted the aircraft laterally. Not far, but far enough. The terrain beneath is not what was expected. It is higher. The descent continues. Small control inputs maintain stability, but the aircraft performance has changed. Ice accumulation has increased. Lift is reduced. To maintain the same descent profile, additional control input is required. The difference is slight, detectable, but only through careful attention. In an environment where attention is divided, such changes do not always register immediately. Engine performance remains consistent. No loss of power. No irregular vibration. The engine provides reassurance. It suggests that the aircraft is functioning as intended, and in a mechanical sense, it is. Time passes, not in Mach intervals, but in continuity. The expected visual cues, terrain features, breaks in cloud, navigation references, do not appear, but absence in this environment is not unusual. Cloud obscures everything. The lack of confirmation does not immediately indicate error. The aircraft descends further. Altitude now approaches a threshold where terrain clearance depends entirely on positional accuracy. But position has not been verified, only assumed. There is a moment, brief, easily overlooked, where expectation and reality begin to diverge more rapidly. The pilot anticipates reaching a lower elevation zone. Instead, the aircraft is approaching rising ground, still hidden, still silent. The instruments do not indicate terrain. They cannot. They only reflect the aircraft's internal state. Pressure, altitude, airspeed, heading. None of these measure distance to the ground below. The first true indication is not visual. It is tactile. A subtle change in airflow. A slight increase in turbulence. Not from weather, but from interacting with terrain below the cloud layer. Rising air currents. Irregular, but not severe. They suggest proximity, but not definitively. A correction may begin. A slight adjustment, perhaps a reduction in descent rate. But without confirmation, it is cautious, limited. The aircraft continues downward. Then, the cloud layer thins. Not enough to provide full visibility, only enough to introduce contrast. A variation in gray, a suggestion of depth, and within that form, terrain emerges without transition. There is no gradual reveal, no distant horizon, only immediate proximity. Dark, undefined shapes, rising into view. Distance is difficult to judge, but it is insufficient. Reaction is immediate. Control inputs increase. The nose is raised. Engine power may be advanced, if available, but the aircraft is no longer operating within its original performance margin. ICE's altered lift characteristics. Climb response is reduced. The aircraft does not respond as quickly as expected. Seconds compress. There is no time for recalculation, only response. The terrain continues to rise. The aircraft attempts to outclimb it, but the margin, already narrow, has been consumed. There is no loss of control, no structural failure, no sudden deviation. The aircraft remains stable. It is flying, precisely as commanded, just not where it should be. The final moment is defined not by chaos, but by inevitability. Contact with terrain occurs at control flight. Forward velocity remains. Attitude is stable. There is no abrupt maneuver beyond the final attempt to climb. The sequence ends without warning systems, without alerts, without external intervention. Only the convergence of assumed position, unseen terrain, reduced performance. The engine, until the final second, continues. Steady, consistent, unaware. The aircraft does not arrive. There is no immediate alarm. In this era, absence is not unusual. Flights are not continuously tracked. There are no radar returns to disappear, no transponders to fall silent. Only an expected time of arrival, and when that time passes, uncertainty begins. At first, the delay is procedural. Weather may have slowed progress. A diversion may have been necessary. Communication gaps are common. Time extends. Minutes become an hour, then more. Concern develops gradually. The destination airfield makes inquiries. Intermediate stations are contacted. if any, exists along the route. No confirmed sighting. No transmission received. The aircraft has not reported position beyond its last known estimate, and that estimate, as it now becomes clear, may not be reliable. The search begins without precision. There is no defined location to investigate, only a projected path, a line drawn from departure to destination, adjusted for estimated speed and heading. But that line assumes accuracy. It does not account for drift. Search aircraft may be dispatched, if available, but they face the same limitations. Restricted visibility, limited navigation aids, vast, indistinct terrain. Ground teams move outward from known points, roads, settlements, rail lines. The search area expands quickly, not in measured increments, but in uncertainty. Weather continues to interfere. Cloud layers that conceal the aircraft in flight now conceal its absence. A crash site, even in daylight, is difficult to detect from the air. Wreckage does not always contrast sharply with terrain, especially in mountainous or forested regions. Time passes, days, in some cases. The search becomes less about interception and more about discovery. Eventually, the site is located, not through instrumentation, but through proximity. A ground party, a passing observer, or a search crew operating at low altitude. The aircraft is found where it came to rest, not far from its intended route, but far enough that assumptions failed. The condition of the wreckage provides initial clarity. The aircraft impacted terrain while under control. There is no widespread distribution of debris that would indicate mid-air breakup. No evidence of explosion prior to impact. The angle of contact suggests forward motion, not descent out of control. From this, an early conclusion begins to form. The aircraft was functioning. The engine, where recoverable, shows no indication of pre-impact failure. Control surfaces, though damaged by impact, do not suggest in-flight separation. The structure remained intact until contact with terrain. Attention shifts to navigation. Where was the aircraft believed to be? And where was it actually? This question is difficult to answer definitively. There are no flight data recorders, no cockpit voice recordings, no continuous positional logs, only fragments, departure time, estimated ground speed, intended heading, last reported or assumed position. From these, investigators reconstruct a probable path, not exact, but sufficient to identify deviation. Wind becomes a central factor. Meteorological records, limited though they are, indicate crosswinds at altitude, stronger than anticipated, variable across the route. Such conditions would have produced lateral drift, gradual, unnoticed without external reference. The conclusion develops. The aircraft maintained its heading, but not its track. Terrain analysis follows. The crash site lies within elevated ground, higher than surrounding regions. In clear conditions, it would have been visible. In cloud, it was not. The descent profile is examined. Why did the aircraft descend at that point? The answer aligns with standard procedure. Based on expected position, descent would have been appropriate, but the expectation was incorrect. Instrument limitations are considered. The altimeter functioned within its design, but it measures pressure altitude, not terrain clearance. In rising terrain, this distinction is critical. Icing is evaluated. Evidence suggests accumulation, not catastrophic, but sufficient to degrade performance, reducing climb capability at a moment when climb was required. No single cause is identified. Instead, the investigation reveals a sequence. Navigational drift due to uncorrected wind, descent based on assumed position, terrain obscured by cloud, reduced performance due to icing, absence of terrain awareness. Each factor alone is manageable. Combined, they are not. The language of the findings reflects the limitations of the time. There is no standardized classification system, no formal term such as controlled flight into terrain. But the concept is present. An aircraft, under control, flown into terrain due to lack of situational awareness. The impact of the accident extends beyond the site itself. Operators review procedures. Routes are reevaluated. Questions are raised. Should minimum altitude be increased? Should flights continue and reduce visibility? Can navigation be improved? Answers are not immediate, but the process begins. In the absence of precise data, progress is incremental. Lessons are inferred. Patterns are recognized only after repetition. This accident is not isolated. It is part of a broader pattern emerging in early aviation. A pattern defined not by dramatic failure, but by quiet miscalculation. The investigation does not conclude with certainty. It concludes with understanding. Partial, but sufficient to indicate that the system, as it exists, is incomplete, and that incompleteness has consequences. The flight ended quietly. No explosion. No sudden catastrophic failure. Only a series of small divergences, imperceptible in isolation, that converge to define consequence. In the aftermath, the aviation community began to recognize patterns. Controlled flight into terrain, though not yet formally named, emerged as a recurrent hazard. It was a lesson in alignment between pilot perception and reality, between instruments and environment, between procedural expectation and operational uncertainty. Aircraft design evolved in response. Cockpits were gradually equipped with artificial horizons, providing a reliable reference for attitude when visual cues failed. Altimeters were calibrated and standardized to account for terrain and pressure variations. Engines were refined to reduce sensitivity to icing and environmental degradation. Redundancy became a principle. No single instrument or single pilot judgment would alone dictate safe flight. Navigation systems were strengthened. Lighted beacons were extended along major routes. Radio navigation became more reliable. Charts included terrain elevation with increased precision. And in time, airways were formalized, minimum altitudes codified. Training shifted. Pilots were educated in instrument flight rules, emphasizing reliance on instruments when visual references aren't available. Standard procedures for cloud flight were introduced. Crew coordination, later formalized as crew resource management, became recognized as essential. Regulations followed. Authorities mandated equipment, procedures, and minimum standards. The aim was not to eliminate risk entirely. No system can. The aim was to reduce uncertainty, to bring the previously invisible into measurable terms. In hindsight, the accident is not a story of error. It is a story of limitation, of a system in transition, of skill operating at the edge of available tools, of an environment indifferent to expectation. The lessons endure. Pilots today rely on technologies, procedures, and knowledge absent in the 1920s and 1930s. Yet the principle remains. Flight is not defined by what is seen, but by what is known and what is assumed. Margin, redundancy, and awareness form the foundation of safety. And when those margins are preserved, aircraft operate reliably even in conditions that once proved fatal. The flight ends not with spectacle, but with reflection, a quiet acknowledgement. Progress in aviation is measured not only by achievement, but by the understanding of past limitations. Each accident informs the next procedure. Each lesson, in turn, shapes safer skies. The legacy is cumulative. It is methodical. It is enduring.